Have you ever told someone, oh, just walk 3 blocks that way and take a left? Well, if you have, you've actually been speaking a secret language. It's the language of vectors, and it's what describes pretty much everything in our physical world. Today, we're going to decode that language, a language that is absolutely critical for physics, for engineering, and yeah, even for just finding your way home.
So here's our game plan. We're going to start with the one simple idea that makes a vector so much more than just a regular number. Then we'll get into the visual way of combining them, literally drawing arrows. After that, we'll unlock their true power with something called components, get a quick peek at what happens when you multiply them, and by the end, you'll see why vectors are, no joke, the language of reality itself.
All right, first up, what is it that makes a vector so special? Let's dive right in and figure that out.
Let's just stop and think about this for a second. If I told you I traveled 5 miles, do you have any clue where I am? Of course not. You're missing half the story. You know the how much, but you don't know the which way. You're missing the vector. And this slide right here just nails that difference perfectly. Over on the left, you've got what we call scalars. They're just numbers. That's it. Temperature, mass, or just 5 miles. They only answer the question, how much? But on the right, you've got vectors. And vectors tell the whole story. They've got a magnitude and a direction. It's not just 5 miles, it's 5 miles north. Now that is a complete instruction.
So let's meet our first and simplest vector, the displacement vector. The best way to think about it is like an arrow on a treasure map. It points directly from where you started, point A, to where you ended up, point B. The length of that arrow tells you the distance, and the direction it's pointing, well, that's your direction. Simple as that.
Okay, this slide shows two really important ideas about vectors. First, take a look at those 3 arrows on the left. Believe it or not, those are all the exact same vector. Why? Because they have the same length and they're pointing the same way. This means you can slide a vector anywhere you want, and as long as you don't stretch it or rotate it, it's still the same vector. Second, that diagram on the right shows that the final displacement vector only cares about your start and end points. It doesn't care about the wandering, scenic route you took to get there.
All right, so we get what a vector is, but what do you do with them? How do you combine them? Well, let's start with the most intuitive way there is, by just adding the arrows together.
Here's how you do it visually. It's called the head-to-tail method, and it's super simple. Imagine you walk along the path of vector A. Then, right where you stop, you immediately walk along the path of vector B. Your total trip, the final result, is the single vector S that goes straight from where you very first started to where you finally ended up. You're just connecting the arrows, tip to tip.
And what's cool is that, just like with regular numbers, vector addition has a couple of superpowers. The first one is called the commutative law. All that means is that adding A plus B gets you to the exact same spot as adding B plus A. The order you add them in totally doesn't matter. The second one is the associative law, which just means if you have to add 3 vectors, it doesn't matter which 2 you add together first. The final result is always going to be the same.
But what about subtraction? You might think that's going to be complicated, but it's actually incredibly easy. See, subtracting a vector is just adding its opposite. A negative vector, like minus b you see on the left, has the exact same length as the original, it just points in the 180-degree opposite direction. So to find a minus b, you just flip b around to make it minus b, and then add them together like we just learned. Problem solved.
Okay, time for a little puzzle. Imagine you're on an orienteering course, and you have 3 paths you can take, A, B, and C. Your goal is to combine these paths to end up as far away from your base camp as possible. How would you do it? Well, if you play around with the combinations, you'd quickly find the answer. You go along path A, then path B, and then you take the opposite of path C. You're literally using vector math to find the best possible route.
You know, drawing arrows is great for getting the basic idea, but for doing real physics, we need something a little more precise, a little more powerful. This is where we level up. It's time for vector components, and trust me, these are a total game changer.
So the big idea here is that we can break any vector down into simpler pieces. Picture the vector A like it's a stick. Now imagine a light shining straight down from above. The shadow that stick casts on the x-axis, that's its x component. And if a light shines from the side, the shadow it casts on the y-axis is its y component. These two shadows, AX and AY, contain all the information of the original vector, but they're way easier to work with.
So how do we find the exact length of those shadows? You're not going to believe it. It's just some basic high school trick. If you know the vector's total length, its magnitude, A, and the angle it's pointing at, theta, then the x component is just A times the cosine of that angle, and the y component is A times the sine. That's it. That's the secret code.
Now, those components we just found, AX and AY, are just numbers. They tell us how much, but they don't have any direction. So how do we fix that? We use these brilliant little things called unit vectors. Meet I hat, j hat, and k hat. Their length is exactly 1. Their only job in the entire universe is to point. I hat points along the x-axis, j hat points along the y-axis, and k hat points along the z-axis. They are pure direction.
Think of these unit vectors like they're building blocks. We can now write any vector as a really simple recipe. You take your x component ingredient and you give it the x direction with I hat. Then you add your y component ingredient and give it the y direction with j hat. This is called unit vector notation, and it's the standard, most powerful way to work with vectors. So why on earth did we go through all that trouble? Because of this. It makes adding vectors ridiculously easy. We've turned a tricky geometry problem into simple arithmetic. The process is always the same. Step 1, break every single vector down into its x and y components. Step 2, add up all the x parts, and then, separately, add up all the y parts. And that's it. You're done. You now have the x and y components of your final answer. Let's see this in action with one of the coolest examples in all of physics. Seriously. A desert ant wanders around on what looks like a completely random haphazard path. But the second it finds food and needs to go home, it turns and runs in a perfectly straight line right back to its nest. How in the world does it do that? It's doing vector addition in its tiny little brain.
So here's the ant's secret. Every little leg of its journey is a displacement vector. By breaking each of those vectors down into its east-west component and its north-south component, and then just adding up the columns, the ant can figure out its total change in position from the nest. It takes that chaotic path and turns it into a neatly organized set of numbers. So that final sum tells the ant its net displacement, d net, which points from its nest to its current location. To get home, all it needs to do is follow the vector d home, which is just the exact opposite of its displacement. By adding components, that ant turns a complicated, winding journey into a single, direct path. Chaos becomes order. It's amazing. We've got addition and subtraction down, so now let's move on to multiplication. But here's where it gets a little weird, in a good way. It turns out there isn't just one way to multiply vectors. There are two, and they do completely different things.
So first up on the left, we have the scalar product, or the dot product. When you take the dot product of two vectors, you don't get another vector. You just get a single number, a scalar. This is really useful for things like calculating the work done by a force. Then on the right, we have the vector product, or cross product. When you do this, you get a brand new vector that points perpendicular to the two you started with. This is absolutely essential for understanding anything that spins or rotates.
So how do you figure out the direction of that new vector from a cross product? You use this really neat trick called the right-hand rule. Okay, get your right hand ready. You point your fingers in the direction of the first vector, A. Then you curl your fingers toward the second vector, B. And wherever your thumb is pointing, that's the direction of the result. It's a fantastic little shortcut that gets you the right answer every single time.
Okay, for our last section, let's just pull back for a second and talk about why all this matters so much. This isn't just some neat math trick. This is the very language that physics is written in. This slide shows a really deep and beautiful idea. Do you see how, if we rotate our point of view, our coordinate axes, the numbers for the components change, but the vector itself, that physical arrow representing a force or a velocity, it stays exactly the same? That's because the vector describes reality, and reality doesn't care which angle we choose to look at it from.
At their heart, vectors are powerful because they're an incredibly efficient shorthand for reality. When a physicist writes a single elegant vector equation like F equals ma, they're not just writing one equation, they're actually writing three equations all at once, one for the x direction, one for the y, and one for the z. It's a stunningly compact and profound way to describe the laws that govern our universe.
So, we've learned the basics. We've decoded the language of vectors, from the push of the wind on your face to the velocity of a planet in orbit. The world is just full of these quantities that have both a size and a direction. So my question to you is, now that you can see them everywhere, what are you going to use this new language to describe?